we can see
Yes, you can see it.
Yeah.
Thank you for arranging this from Tech20. Autonomous drilling, that is the end game. And we're going to talk a little bit, as Benjamin Franklin said, well done is better than well said. A lot of players is saying a lot in this game, and we hope we can show you some of the things that has been done and not only said. Just quickly, Sekal was acquired by Sumitomo Corporation last year. The technology is based from research at Norse, formerly called IRIS, and it started with players like Equinor, Chevron, Eni, and BP approaching Norse and wanted to embark on a project for autonomous drilling 20 years ago. Just a flash of the clients we're working with today. I won't go into detail here, but it's a global collection of clients. The portfolio we have of software today is all based on modeling, physical models. So it's hydraulic models, it's mechanical models, torque and drag models, mechanical models, and thermodynamical models. These are coupled together and work interactive together. So they are also transient, so that they are able to model in real time. To run these models, you need to configure the models with the well you're going to drill. And this is something that surprisingly is very often done manually today. But we see more and more operators are now moving ahead to getting themselves a digital platform that could actually give us the well plan, the digital operation procedure, etc., that we need to run the models. We can still run the models, but then we do that as a manual input. Real-time data comes from the rig, typically for the application that we call drill scene. It is taken from a WithML source, could be any WithML server, and then we use that to run the models, and we present results in the application called drill scene. So drill scene is in a way drilling a digital well or a digital twin, if you want to express it like that. So as an example, if you model the standpipe pressure and you look at the measured standpipe pressure, and you could see a very minor deviation maybe on the measured standpipe pressure, that could be then an indication of a pipe washout. So drill scene is for looking at long-term trends, building roadmaps, but also showing you transient curves of, for example, how the ECD is behaving along the whole wellbore. And if the configuration data and the WithML data are good, that is pretty accurate. And as we experience these days, this is getting really, really good. If you, for example, in drill scene, discover that you are about to get a hole cleaning issue where you are building cuttings beds and you are loading cuttings in your annulus, you could, for example, then drop that to the simulator called DrillExpect. And then you could do simulation like look ahead, fast forward look ahead. So if it's a hole cleaning issue, you could then start playing with RPM and flow to see which are the parameters that could cure the issue that you're about to get. When you move to automation, we still use the same models, but then we are connected directly to the heart of the rig, which is the drilling control system. So currently we have integrated with both NOV and MH Wirth, but we could, in theory, integrate with any drilling control system. It's a closed loop where we calculate, take values from the drilling control system, and we calculate the limits that the wellbore tolerates in real time, and we write those limits back to the drilling control system. So that the driller, in the same way as you have traction control on your car, if he tries, for example, to trip faster than the well could tolerate, then he will be limited by the drilling control system that has got the values. That is called safeguarding in our system. When you have the safeguards active, you can then start run autonomous functions, like, for example, starting and stopping the mud pumps. I'll get a bit further back to that. On top of this, we have a screen that is currently under a massive development. It's called DrillAware, and that is a screen that we could put in front of any relevant user. It could be the driller, it could be a real-time operation center, and could also be a drilling engineer that is just planning a well. So the experience value proposition that we see is that the elements that we address is the NPT and the safety. So everyone, of course, wants to secure well integrity and make sure that that everyone stays within the pressure window. So it's about avoiding swap, avoiding collapse, avoiding surge. So you see there on the graph that the modeled ECD and ESD can be shown at any time in real time. And you don't even have to have wired pipe for that to be shown like that. Next thing is that you don't want to have your pipe stuck. And if we look into statistics from DrillScene, DrillScene has been applied for more than 350 wells at the moment. And we got some statistics from the Norwegian Petroleum Directorate, and we started looking into how many sidetracks, technical sidetracks, has it been with DrillScene being used compared to the statistics before DrillScene was used. And statistically, we can then see that we have saved 77 technical sidetracks. And one of the clients, which is an offshore operator, they value or says that the average cost of a sidetrack is $7.5 million. If you do the very big math here, that's $580 million in statistical sidetracks that has not taken place. Another element is that you don't want your pipe to fail. And we have a lot of cases where we have guided the client that you most likely have a pipe washout situation. And then it's up to the client whether to trip out or to look further into if that is really an issue. So the example picture you see there, we have had a lot of these cases, and you can imagine the cost of that should that twist off, and you have at best a successful fishing job. That's the NPT element. If we go over to the ILT, or invisible lost time elements, when you do modeling and you have good input and configuration as we have today, then you know the limits of your wellbore. And that is, of course, much easier than to optimize. So you can then better optimize tripping and casing running speed. You can have a view of how is your cutting load in your wellbore. Are you building cuttings bed? How is the cuttings in suspension in your mud, in your wellbore, and where are they? And of course, ROP, you can then use these models to guide the ROP in such a way that you're not running necessarily at the maximum ROP, but you're running at that ROP that makes sure that you stay in your window and you maintain sufficient cuttings transport. DrillTronics is the drilling automation tool, and that was first time installed on Statfjord C in 2013. Since then, several floaters and also fixed installations has taken DrillTronics on board. And at the moment, there has been 8 of these installations. Safeguarding, what is that? Well, safeguarding is calculating what is the maximum pump acceleration that you could have right now. What is the maximum pump rate you could have? What is the maximum pump pressure you could have? What are the maximum weights you could have on set down and over pull? And what's the maximum torque? And also, what is the velocity and acceleration you could have of the drill string or the casing to avoid surging and swabbing? These are the elements that are calculated on the signals we get from the drilling control system, and then it's sent back to the drilling control system to make sure that the driller stays within this envelope. Having this in place, which we call DrillTronics Core or safeguards, that's the one that addresses the NPT elements. On top of that, you then have automatic pump start and stop. You have automatic reciprocation, you have automatic back reaming, automatic tripping, casing running, and we are actually showing next week, together with NOV and Norse, the new function called Smart Auto ROP that I just talked about earlier. This can be integrated with systems like Novos, Deal, and also Lynx, but there's also other systems that could be relevant for such an integration. I'm just going to show you some examples that we have done where we have used cases where something went wrong on the left-hand side. In this case, you see they are tripping out of the hole. They are violating the pore gradient, the red band there, and they are taking an influx. We ran this through DrillTronics just to see what would be the ECD when DrillTronics is applied. And with DrillTronics applied, the tripping speed will be limited so that the ECD is not going below, or ESD is not going below the pore gradient. Similar setup is here by starting the mud pumps. Left-hand side, the driller is very quick on starting the pumps, causing a fracture at the shoe. Whereas you see on the right-hand side that the driller is starting this according to a calculated procedure, making sure that pressure pulses does not go above your weakest point when it comes to fracture. This is another example where we tried to take friction test manually at Statfjord C, and then we did it automatically with DrillTronics. And you see on the left-hand side, it's picking up, rotating, slacking off, and it's not consistent at all. And you can imagine these are frictions that you're building roadmaps on, and then you might wonder, why are your roadmaps not correct? So having friction tests that are consistent is a high value to the client. We have, though, during the last year, made a transient torque and drag model that actually performs the friction test automatically. So you're not in need to do these friction tests if you're running, for example, the transient torque and drag model. Starting the mud pumps, on the left-hand side, you see the driller is trying to ramp up the mud pumps as a procedure that they are used to. In this case, they ramp up to target flow, which is the red average you see in the graph on the left-hand side. It's reaching target about 270 seconds, whereas when you do it with DrillTronics, you reach it about 60 seconds faster. That is not necessarily the main saving here. The main saving is on the left-hand side, there's no safeguards. It's a manual operation. But on the right-hand side, you actually have the safeguards on. Smart Auto ROP, we talked a little bit about that, and that is actually performing automatically drilling of a stand. So it executes automatically ROP performance tests. It controls the weight on bit, the RPM, and the flow rate to optimize the ROP, taking into account cuttings transport, risk of drill string vibration, and also risk of formation washouts while applying real-time safeguards. So this is, as I said, there's going to be for several operators a presentation Tuesday next week together with NOV to show this functionality. We're probably going to set up some extra webinars around this. So if anyone wants to have a look at that, you're welcome, of course, to give us a note on that. The next procedure we are starting to build is actually to look into how could we go from slips to drilling and drilling to slips automatically, and actually tag bottom where we are using our models. Our models take into account the stretch of the string, so it's quite accurate when we are calculating the bottom of the hole and how long the drill string is. So this is a function that is also going to be developed, and NOV is also going to be part of this procedure here. How does it look on your rig? Well, on DrillTronics, we have on the rig, very often in the same cabinet as the drilling control system, or just side of the drilling control system. There is a calculation server. There is 3 embedded PCs from, typically in this case, Siemens. And the only integration point is a gateway PLC to the drilling control system. Then there is an admin client on the rig, and there's another one on shore. I'll end this presentation by showing you a replay, and this is a recent well that has been drilled by an operator in Gulf of Mexico. And in this case here, the well collapsed, and they could not understand what actually happened. So in this case here, you see there is a weak point there with a red band for collapse. And that is at 11.462 pounds per gallon. The mud density at the surface is 11.6, and when they're drilling, the ECD is 12 pounds per gallon. Okay, they stopped the pumps, and they assume that the ESD is then dropping to 11.6, but they are not taking into account temperature effects. So when we did the replay, we see that the ESD was not 11.6, it's actually 11.54 because of the temperature effect. So you're actually pretty close to that collapse limit. So what happens then when they start tripping out of the hole? They trip out rather slowly at 24 feet per minute. And then the ESD is actually dropping to 11.41. And that is causing a swab in that well bore and actually collapsing the well. When we looked into this, we saw that the maximum speed they actually could have had was 10 feet per minute, and then they would not have crossed the boundaries. This well bore was lost, and this is the main reason for us to coming into this client and doing more business with this client. And this is a very good way to, if you have a well that something went wrong in, we can do a replay of that and actually run the well as if it was live, and then we can get back to the client and we can tell the client what could we have seen. That is about 95% of the ways to actually get familiar with the technology using your old well as an example. That is my last slide, so I think I'm in the time zone.
Yeah, that was excellent, Asbjørn. Thanks for that really good overview of what autonomous drilling can do in terms of safeguarding wells. I think for me as well, one thing that kind of occurred to me just as I was listening to your presentation is that we have a lot of data, I guess, nowadays, with surface sensors and downhole tools, and there's a lot of data for drillers to be looking at and monitoring whilst they're drilling a well. So I think from a human factor perspective, anything that we can do to help the drillers with this kind of conscious overload when they're looking at all this data and monitoring and looking after personnel as well, I think's really helpful. So no, that's it's really good. So I just noticed one question coming in there just as you were talking. So I'll just pull it up. So we've got a question in from Carl Jeffrey, and he's saying, how do you handle liability if an accident happens due to the system controlled by your software?
It's a good question, and the clients we approach are the operators, and the way the system works is you either have the drilling pulling the joysticks and causing an issue that might end up with something going wrong. So what we're actually doing is that we, instead of sending the joystick signal, is actually we are overriding these signals, but there are still all the systems in place that the drilling control system is taking care of, like anti-collision, and machinery cannot perform better, of course, than the limitation of the machines, etc. So that is an agreement that we go in with the operator, and also when we do it directly with the rig owner, we enter that into the agreements that we are there as a kind of a system that is more or less just replacing the signals that's coming from the driller. But it sometimes it could be a question that we spend some time on. Absolutely.
Great. And I've got one more question in the chat here from Craig Hodge, and he's saying, "Hi Asbjørn, with increased automation and connectivity, do you see increased opportunities for making operations more remote? For example, do you see the possibility of the drilling control station being moved onshore? And if not, what do you think the biggest barriers to this?"
Well, it's a conservative industry, so I'm not sure how that's going to take place. But if we talk about technology, yes, it's there to do it today, I think. But you need to have a lot of players playing together for making that happen, I think. As we see it, we see that what can we do today? Well, we can stop and start the mud pumps, fully autonomous. But when we come out with these kind of functionality, the driller often says, well, I don't want to start and stop the mud pumps in one go. I want to start the mud pumps, making sure that I break the gel, I activate the MWD, etc. So it's still a way to go there, but yes, we could do quite a lot already on that, but it also depends on the conservative industry if they are adopting it.
Excellent. So another question here from Malcolm Banks. So do you believe automation has the potential to reduce offshore manning levels? And if so, roughly by how many?
It's related to the previous question. It has the potential, yes. If it's going to happen, if you look at an airline today, there's still a pilot there. So I think the focus currently is how can we do these procedures safe and avoid the big NPTs and optimize. I think there will still be a driller sitting in that chair for a long time.
Yeah. And another question here from Dave Wilkinson. Do other similar systems exist?
To our knowledge, for the clients we have worked with, we don't know about any other system that is currently competing with a model-based automation tool like DrillTronics. There are other systems, of course, competing with systems like DrillScene and the simulator DrillExpect. Excellent.
So this next person that's asked the question, I'm going to apologize if I pronounce your name wrong. Is it Phantomapat B? And he's asking, do you have any plan for a fully autonomous drilling with also robots at the rig?
Yeah, that is, if you look at, there's a project at Norse, which is called DADPC, and that is just what they are trying to show. They are trying to see if they can use some of the machineries, like from Neighbors. You have this robotic drilling robot that have this arm that actually work on the rig, and more in machinery there together with DrillTronics. So that is actually something they are trying to show in that project, and it looks like they have got quite far on that project.
Excellent. And just Asbjørn, you spoke a little bit about running casing and tubing and things. For completions in general, can we use the same model? Would, for instance, DrillTronics still be applicable when we're in a completion phase to prevent any wellbore?
As long as you're moving something in and out of the wellbore, you could. We have been looking into cementing and stuff like that. Currently, we can do some there, but there's still some way to go with that.
Yeah, excellent. Another question just came in here, Asbjørn, from Carl Jeffrey. He's saying, just using modeling to support human operators sounds like very common sense, sensible move, making life easier and safer. What are the main obstacles to this, do you think?
Yeah, I would say the way we are looking further now is that using physical models, for example, when you are modeling cuttings transport, that is a very, very advanced modeling that takes place to actually understand that and to make that work. And we see that we could probably now get more out of that by also putting machine learning on top of that. So it probably would be more going in the direction of using other techniques so that you could make sure that you can verify, for example, the signals you're getting in, making sure that you are totally correctly configured. I spoke about that in the beginning. As an operator, it's very important that every operator starts thinking about how is my digital platform, because in the future, when you're going to use these kind of tools, that would help a lot to make sure that you could actually get all the benefits out of these kind of systems.
Yeah. So just, you mentioned that during the presentation, Asbjørn, about the smart ROP function, which is great. What's the next steps as you see it? What are you guys maybe currently looking at that you think's the next phase of autonomous drilling for Sekal?
Well, first of all, it's going to be making sure that these sequences that's actually when you're drilling a well, that we can do them autonomous. And then, of course, we have to work together with the equipment manufacturers, making sure that it works together with them. That's why we're also working with MH and NOV. The next thing I think that is exciting is to look into, because we just had a client and they were drilling and following the procedures, very good at following the procedures. They had no NPTs, but they were drilling very slowly. And we had a look into, for example, after each stand being drilled, they back reamed. And they reamed the whole stand. But it was totally clean. All the indications showed that the wellbore was clean. So if you start adding up that number of minutes that you used on that reaming, it's actually ended up for the 4 wells, it was about $2 million for that rig. So I think what we see is that we probably will do more simulations where we are looking at optimum, so that if we see that there is a hole cleaning issue, we'll actually make sure that it starts automatically to clean up. If not, we're going to override some of the drilling procedures so that you're not doing a bottoms off it if it's not needed. But that's not being done currently.
Okay, great. One question is coming from Malcolm Banks, and he's saying, can the system be installed on all rigs, or is there a minimum control system requirement?
Yeah, if it's a DrillView or a NOV cyber-based Amphion system there, or any Cameron system, Hoistman system, shouldn't be any issues. If it's an old rig, typically we, as a rule of thumb, we say, okay, if it's older than 2005, it starts getting tricky. But then again, there are some modern old rigs as well, so it would depend, but it is possible, yes, for a lot of rigs.
Great. So I'm just having a look to see if we have any more questions. Just to everybody that's online, like I'd said at the beginning of the presentation, if you want to ask a question yourself, just raise your hand and I'll unmute you and you can ask, or yeah, just type it in like you have been doing to the chat function there. I think one thing that stands out as well for me, Asbjørn, is just we've been speaking a lot about how autonomous drilling can help us improve performance and avoid us losing wells. But one thing I guess that kind of ties into that, the I guess indirect benefit that has to carbon or greenhouse gas reduction, and obviously the industry looking at net zero and looking to move towards net zero. part of that has to be performance improvement based, because obviously less time you spend drilling a well or re-drilling a well, you're having less an effect in producing greenhouse gases. Is that something that Sekal looks at maybe trying to quantify in terms of the time you're saving operators?
It is being looked at, and we actually, to make it more objective, it's something that we have asked the Research Institute to look into. And if you're thinking about a floater or a semi-sub, might have a spendage of 40 ton of fuel a day. And if you could save, let's say you could save 20-25 days, you can start doing the math and actually calculate what is the carbon footprint on that. So that's actually being done, and it's going to be published in at least Norwegian magazines from Norse. Yeah, I think they might have actually already have published it, and I haven't seen it yet. Yeah.
Yeah, that'd be interesting to see. And maybe if you do find that, Asbjørn, maybe for the LinkedIn, you can maybe put a link there for anybody that's interested to go in and have a look. I'd certainly be interested to see that. Can I just ask the audience, is there any more questions that anybody would like to ask Asbjørn? Well, I think we're all quite quiet there. So again, Asbjørn, I thought that was really interesting, and we got some really good questions in there from the audience, and I really enjoyed your presentation. So thank you very much for agreeing to do that and coming on and letting us hear a little bit about drill scene and DrillTronics. Just for the audience there's a QR code for you to scan, and it takes you to the upcoming Tech20 schedule. And the next Tech20 is scheduled for next Friday at 11 AM. And also, it'd be really helpful if you could complete the survey at the end of the webinar, just to give us some feedback on the Tech20 events, as we always look to improve what we're doing. And remember to head over to the LinkedIn page to continue discussions with Asbjørn. And that's it, we'll wrap up there. So thanks everybody for joining us today, and I hope everybody has a good weekend. Thank you.
Thank you.
Thanks, Asbjørn.